Okay, so we were discussing NumPy arrays, and one part that we didn't get to last time was how they are used in plotting. Okay, so I'll discuss a very simple. You can do much better plots and more intricate ones than the one I'll show you here, but we should at least know the basic part, and then you can read the documentation. Okay, so we're going to use plotting, and that's done using the pyplot, which lives inside of matplotlib. So, and there are other plotting programs, but I'm saying let's learn one here. What we do is essentially we plot arrays against arrays. So I'm going to need NumPy in order to get the arrays. So let's import NumPy, and we'll import NumPy as NP for short. And I also need the pyplot program. So I'm going to, the pyplot submodule. So I'm going to import that as import matplotlib.pyplot as PLT for shorthand. Okay. That way I don't have to refer to the long name when I need it. Okay. All right. So let's say our aim in this little bit of the lecture is to get a plot of sine of x versus x with a few bells and whistles like a legend, defining the thickness of the line, the color, and so on. Okay. So the basic idea is we're going to have a NumPy plot for x. We're going to have a NumPy plot. Sorry, we're going to have a NumPy array for x. We're going to have a NumPy array for sine of x. We're going to put both these things into pyplot, and pyplot will hopefully we'll feed it some parameters also, and then pyplot will give us a nice plot of sine of x versus x. Okay, so first, let's create a NumPy array of x values. And one way of doing that is to use the linspace constructor, which exists in NumPy. So I'm going to say x is equal to numpy.linspace of, I feed it where the start value is 0, the stop value is 2pi, and a value for pi lives inside of NumPy. So I'm going to say 2 times np.pi. And then 100 means I want 100 points. And I want the endpoint to be included. So I'm going to set endpoint equals true. Now that's the default anyways. But just to be explicit, we're going to say that endpoint is equal to true. Maybe for some application, you would want that to be false. You wouldn't want the last point to be included because the function is undefined at the last point or some such. Okay. So now for every value in x, I want the sign of that value. Okay. So the nice thing about NumPy is that if you feed an array into the sign function, it takes the sign of each element of that array. Okay. So element-wise. So we're going to let y equal npi times sine of x. So x consists of x values from 0 to 2pi, and y consists of the signs of those values. Okay. So now we're going to create a plot of y versus x, a very simple thing. We say plt.plot, the plot method lives inside of plt. So what's on the horizontal axis? It's x. What's on the vertical axis? It's the values y. So plt.plot of x comma y, and it gives me a plot. Is that okay so far? Yeah. Someone has a question?
Professor, remember in last class we were sort of wondering what if you want the first element to be
Yeah,
not included.
yes.
Uh, is it possible to make like line space arrays backwards? Let's say from 2 pi to 0 and just do endpoint is equals to
Um,
false.
yeah, I think it might be, or it may be not in linspace, but there are constructors that will do that. I can't remember whether it's in linspace or not.
All right, thank you. I'll look it up in the documentation.
Yeah. Okay, so that's my basic thing. And then I say, well, okay. Okay, now there's another thing that you should know. plt.show with no arguments means show the plot on the screen. Now, in this case, the plot has come up on the screen anyways. But in some cases, you might be doing some manipulations and you may not actually be seeing the plot. So at the point where you want to see the plot and it's not showing, then plt.show will do that for you. Okay. All right. Now let's say that I want to change the color. Okay. So I can feed it a color, right? And so plt.plot x comma y as we had before. And this time, instead of resorting to the default color, which seems to be blue here, I'm going to say, no, I want that color parameter to be set equal to red. So if you do that, you get a plot, and the curve of the graph is now in red, right? And if you read the documentations, then it will tell you the other colors that are available. Presumably they would have green and black at least, but there might be more than those. Okay. And of course, color is written in the American fashion, COLOR. Okay. Now, let's say we want to change the line width. If you have weak eyes like mine and you don't like those thin lines, you'd like to set them to be bigger, then what we can do is we can say plt.plot x comma y as before, the horizontal and the vertical values, set the color, let's say to green this time, and let's send, now there's another parameter called line width, and I've decided to make it 3.0. If you divide it, maybe you want to make it 5.0 or something. Okay, so there you go. Another option is line styles. And maybe you want dots, or maybe you want crosses, or some other type of style for the line. Okay, so pld.plot, the horizontal values, the vertical values. Now it's up to you. Set the color, this time to blue. Set the line width, I've made it thicker, 5.0. And I have to design a line style. Okay, so look in the documentation for what the options are. One of the options is dashed. So if I use that and I run that command, I get something that looks like this. Okay. Now, if you're going to make a graph, it's nice if there should be a label, right? If there should be a label. And okay, so all right. So right. Okay, I guess we'll get to the label later. Okay, there's another example. This was dashed, and this was dash dot. Right, slightly different format for the graph curve. Okay, now let's set the legend. We have the plt.plot, horizontal values, vertical values, set the color to green. Maybe the line width is 1.0. Let's set the line style to dash dot. And let's set the legend to be sign, right? The string sign. And now, so plot.legend, set that property of the plot to be the string sign, and plot.show So it shows the sign, it says sign, and it says that that green dashed curve over there stands for the sign values. Okay. Now that seems, the default seems to be that the legend should be on the upper right, but what if I want to change that to the lower right, for example? So pld.plot, horizontal values, vertical values, y. You can set the color to green. You can set the line width. You can set the line style. And for the legend, you will specify what you want the legend to say. And if you say LOC, that's the location. So the locations are upper right, lower right, upper left, and lower left. So say that the location of the legend should be the lower right, let's say, and then pld.show, and it should show you it should show you something like this. And now the legend is in the lower right. Okay, so now, so you're getting the idea, right? Just the basic is X and Y, and then all these parameters. Okay, so let's add a few things all at once now. Okay, so the plot is X versus Y, right? So, well, Y versus X, but we write the horizontal first, X, and the vertical Y. Now, set the title property of that plot to be sin X versus X, and let's set the font size property of the title to be, say, 25. Okay. Now, I would like the X labels and the Y labels to be a little smaller. So let's say their font sizes will be 18. Let's set the X label to be X, and let's set the Y label to be sin of X. And the plot legend, as before, should be sin, and the location should be to the lower right. Now, plot.show, put all those things to get, put in a plot with all of those properties, and this is the plot that I get. Okay, now let's say that I want something like this. I think that these ticks on the left, on the vertical axis, and the ticks on the bottom axis, 0, 1, 2, 3, 4, 5, 6, those are a little bit busy. The other thing is I would like to mark things like 0, pi over 2, pi, and so on, right? To me, that's more informative when you're dealing with a trigonometric function than 0, 1, 2, 3, 4, 5, 6. Okay, so I can decide how many ticks I want, and I can decide how I want to label them. So let's say on the vertical axis, I only want 3 ticks, and I want them to be labeled -1, 0, and 1, right? And I want the I want if again fewer ticks on the horizontal axis, and I want to be label them in fractions of pi. Okay, as is appropriate for a sine function. Okay, so let's do this, and let's put it all together so we review everything we've done. Okay, I need arrays, so I'm going to import numpy as np. I need pyplot, so I'm going to import matplotlib.pyplot, and I'd like to refer to it as a short form plt, so I import that as plt. Okay, I'm going to set up a bunch of x values, so I can use linspace to do that. The values range from 0 to 2n pi, sorry, 2 pi, pi lives inside of numpy, so 2np.pi. I want 100 of them. And I want to include the endpoint, so I said endpoint equals to true. Even if I don't do that, that's the default, it'll do that anyways. The sine function in numpy will act element wise if you feed it an array. So y equals n pi dot sine of x. Now use pyplot plt dot plot. The horizontal values are x, the vertical values are y. Set the color to red, the line width to 3. You can set the line style. Again, this is one of the options for the line style. We'll set the label to sign. I would like the legend to be on the upper left. Now the ticks, so there are the x ticks are the ticks on the horizontal axis. The y ticks are the ticks on the other axis. So let's set the x ticks. The x ticks are going to be at 0, pi over 2 pi, 3 pi over 2, and 2 pi. And the way I want them labeled is with 0, pi over 2 pi, 3 pi over 2, 2 pi. There's probably some reason why I have to put an R in front of it. But anyways, you can read the documentation. But this is the way you make the labels. You have R and then the string that you want the label to be. Okay, I want the y ticks to be at -0, 0, and 1. And then plot.show. And I have something like this. Okay. And there's a lot more. Yeah, someone has a question?
Professor, one question. Let's say we want to sort of overlay two graphs, because when we're estimating sort of places to start, it's a good idea to sort of have two graphs there.
Yes.
So can we just add another plot, and when we do plot show, it's going to show both of them? Or is there a different way to accomplish?
Yes, you can do that.
Right. All right, thank you.
Right, you could have an x1 and an arrays x1, x2, and x3 versus y also, right? Okay, so like I said, that you could probably write a book on plotting, but that would be we don't want to go on for too long. So this is just enough that you could produce reasonable plots, for example, for a homework or something. Okay. And now let me hopefully upload the next notebook. Okay, so hopefully you're seeing a notebook that says review NumPy, review scipy, optimize, and intro to scipy.linalg. Is that right?
Yes, sir.
Okay, all right. So before we did a few, we used bisect. We saw how to use bisect, Newton, and fixed point. And we sort of did them with the bare bones calls. So I want to just discuss a few more options that are available to that. So if we look at bisect again, okay, that lives inside of scipy.optimize. So I'm going to import scipy.optimize as optimized. I'm going to need the I'm going to need the cos function, and I'm going to need the sine function in this part of the lecture. So those live in NumPy. There are also sine and cos functions in a module called math. Right. Okay. So I'm going to import NumPy as NP. Okay. Now what I want to do is I want the root of cos squared of x minus 6 plus x. And I'm going to my bisect method and my my Newton method are going to need me to define that function. So let's call that function func. And so I'm going to say return cosine lives inside of NumPy. So np dot cos of x squared minus x plus 6. Recall that the bisect method lives inside of scipy.optimize. it requires the function, and it requires the interval that you're going to search on. So we're going to, that's what we're going to feed it. Now, this time what I'd like to do is note over here, there's this new parameter we didn't use last time. It's called full sub output equals true. So it's going to throw out more information than we had before. Okay. And there's another option that we have, and that is to set the maximum number of iterations. So it has a default number of iterations that it uses. And we're going to set the max iter. That means set the max number of iterations to this. In this case, I'm going to set it equal to 10. Okay. So I'm going to try it once with the full output set equal to true, and then I'm going to try it again with the full output equal to true, and with a maximum number of iterations equal to 10. Okay, so if I turn on the full output, this is what I get. I get the result that I wanted. I also get a flag about the convergence, right? It says that it converged. It tells me how many function calls it made. So if you're concerned, for example, you've got you've got a more complicated code than this, right? And you're concerned about how many times the function is being called. Maybe you think it's excessive, your code is too slow or something. So you can see how many times it's being called. You can see how many iterations are made, and you can see what root is produced. Okay, so if you want, you can get more typically you can get more information out of these methods than just with the bare bones call. You can find out more information about what's going on. Okay, now so we tried that, and we also tried it with, we asked that it be done with the maximum number of iterations set equal to 10. And now, if we do this, we're going to get an error, and basically it says it failed to converge after 10 iterations. Okay. So, like I said, you can get a lot of information out of these things typically, and this one failed to converge. It tells you that it's failed to converge. Okay. For some reason, I'm having trouble running Python 3 on my machine right now. So this is all being done on Colab, Google's Colab. Okay, so you can see it can, if it's convenient for you, maybe that's another way of running your notebooks. Okay. Any questions so far? Okay.
How
All right.
can we see further information about some packages in Python? Like what options are available for certain type, like label dashed line, some and other line? How can we get that information?
Oh, sure. So that would be that would be in the proper documentation. So if you, for example, if you were to Google matplotlib.pyplot in the package that you're using, probably the first hit on Google will be the documentation, and the documentation will tell you all the options. Okay.
So can we also find in Python server lab like editor book?
Yeah, sure. Depending upon which one you're using, for example, I've run this in Colab, and what it's telling me right now is here's a link, and if you want to know about this error, you can click on this, and it will it will search Stack Overflow to find out any information that people have put up about this particular error, for example.
Okay.
Right. So the information you can get on from your editor will depend upon exactly which editor you're using. Okay. All right. So let's see some of the options for Newton that we didn't discuss the last time. Okay. So the way we did it with Newton, I needed the function, I needed its derivative, and I needed an initial guess, right? So I've already, let's use the same function that we've been using before. I already have the function defined. Let me define its derivative. I'll call it f prime. So def f prime of x as minus 2 np dot cos of x. Remember to use the chain rule times np dot sine of x minus 1.0. So hopefully that's the derivative. And that's what I want to return. Okay, and I need an initial guess. I'm kind of cheating. I already know that it's near 6. So, okay, let x0 equal 6. Okay, now we're ready to call the method. Okay, as we did before, we say optimize.Newton. It needs the function, it needs the initial guess, and it needs the derivative. And so you print the result. And if I put that result into the function, it's supposed to be a root of that function, so it should give me something close to 0. So it gives me the result, 6.76, and so on. And it claims that I feed this into the function, it returns 0. Okay, that's basically what we did the last time. Okay. Now, there's a variation of the Newton's method called the secant method. And that occurs if you don't specify the derivative. So I don't know, maybe the derivative is very complicated, or I forgot how to do it, or I'm just lazy, or whatever. For whatever reason, I don't want to specify the derivative. So I can use an alternate, a variation of this method, where it sort of uses secant lines as an slopes of secant lines as an approximation to the derivative. And if you're going to do that, if you're approximating derivatives, then it will approximate the derivative for you. You don't need to do it, and you can simply omit the definition of the derivative function. Okay, so if you drop out that f prime and you just feed it the function and x0, it says I'm looking for it. Newton will, yeah, there's a question.
Professor, would this sort of add to our error, and like would it be a significant?
Yeah, possibly. Possibly.
Okay.
Okay. So with this way of calling it, if I just call it with the function value and the initial guess, it says, well, you didn't define the derivative, so you must want me to use the Newton secant method. Otherwise, you would have given me the derivative. Okay. So if I use the Newton secant method, I get something called result. We print the result, and function of the result, again, it claims that it's 0. Okay. Now, what other things can you do? One thing would be to set the maximum number of iterations. Something is taking forever. You might want to say, well, look, and you're doing something that's happening repeatedly. It's inside a loop. And it's important that there be some progress, even if it's not the best answer. I want some answer, and I want to keep going. Then you might say something like, okay, max iteration, I don't want it to be more than, say, 100 iterations. Whatever you give me is fine after that. Okay, you might want to set the tolerance. It might be a very sensitive problem, in which case you might want to make the tolerance very tight, or it might be something where it really doesn't matter to you, and you can loosen the tolerance in order to reduce the amount of time that's being spent in the Newton method. Okay. There's another method which is called Haley's method. Haley's method requires a second derivative. Okay. So if you call there's an option to call the Newton's method and also to specify the first and the second derivatives, in which case it's assuming that you're going to use Haley's method. Okay. So as an exercise, you can play around with these options and see what kind of results that you get compared to the results that we had previously. Okay. Fixed point again. So remember, there was a fix underscore point method. You gave it G. G is the thing which is set up in as a fixed point iteration. So you have x equals G of x is a reformulation of your problem with something. And one thing that's happening when you're using fixed point, it's using an acceleration method to get the convergence a little bit faster. If you set the option method equal to iteration, then there is no acceleration going on. And as an exercise, what I'd like you to do is set the maximum iterations to 10, set the method to iteration. You'll see that the convergence fails. So once again, if I show you an example using some method, I probably have not used all the options, all the parameters that are available to you, right? So you want to read the documentation about the methods that are being used. Okay, so now let's get back to our NumPy arrays, and I'll show you a few more things that we didn't have time for before. Okay, so one thing that you can do is, and this might be useful to you. I mean, hopefully we're going to be able to. Hopefully we want to simulate stochastic processes, right? So you need to be able to get arrays of random numbers with particular properties. Okay, so NumPy can help us do that. So one way of, so here's one example. If you want an array of random numbers, so numpy.random.uniform. So you want an array of here -1, 2, and then in brackets 2, 3. What that means is I want numbers that are uniformly distributed between -1 and 2, and I want these arranged in a 2 by 3 NumPy array. So if you do that, it produces a 2 by 3 array of numbers which are taken from a uniform distribution between -1 and 2. Okay. You might want to take them from a normal distribution. That's another option. Okay. So you can look up numpy.random, and you can see all the different kinds of probability distributions from which you could get numbers. Okay. Let's say I've forgotten, or I've got arrays with different types of dimensions. So I can add ndim is a property of any array. So I can take a.ndim, and in this case it returns 2. It tells me that this is a 2-dimensional array. Okay. We've already seen some element-wise operations. Let me show you a few more of them. Let's say I have np.linspace 3, 5, 10. That means go from 3 to 5 inclusively, 10 points, equally spaced. Okay. Now, if I say take square root of x, x isn't a number, x is an array. So if I take the square root of x living in the square root as function living inside of NumPy, that means return an array of the same size where every element has been replaced by its square root. Okay. If I say numpy dot sign of x, that means give me a new array where each element of x has been replaced by its sign. Similarly for cosine, similarly for logarithm, similarly for exponential, exp. Okay, here's a notation you should be aware of. Y equals x plus 2, where x is an array, and a NumPy array means add 2. Give me a new array y, which is each element of x has been replaced by that element plus 2. Okay. And, you know, if we wanted, say, supposing we wanted to plot x versus x squared, so we wanted to plot x squared plus 2x plus 1 versus x, then we have the array x, and then we need to get the y values, the vertical values on our plot. So we can get them like this. If I say x squared, what that, and 2x, what that means is perform that operation element wise for each value of x. Okay, so just like we have exponential of x or e to the x, we could have, say, 2 to the x, the same thing. Okay, we can take the minimum value. So every array has a property min and it has a property max. So we can take a dot min means return me the minimum value of the array A. Y dot max with no argument means return me the minimum value of the array Y. So, is that okay so far? Okay, another thing that you might want to do is to save your arrays. So you've done your work for the day, you want to save it, and then you want to come back the next day and use the same array to do something. You don't want to have to recalculate all the values, right? So this is one way of saving and recovering an array. So np.saveTxt, save text, and one argument is the file that you want to save to, in quotes. So let's call it small a.text. And what array are you saving? In this case, it's the array capital A. Now, I also want to be able to read arrays from a file. So let's say B is equal to MP load text of the string a.text, right? So a.text is the name of a file in which the array A was saved. So this is saying, read that file a.text and put those array values into the array B. Okay, and then so B and A should have the same values, right? So let's print B minus A and check that they are indeed. That gives me the 0, right? Okay, is that okay? All right, transposing A. So there's a function for that. So np.transpose of A will give me the transpose of A. Okay. Trace, you remember what the trace is? Anyone remember what the trace is?
So sum of diagonal entries.
Yeah, so if you have a square matrix, the sum of the diagonal entries is called the trace. Okay, so if I take B, remember dot was for multiplication. So if I take B dot A, that multiplies B times A, and it gives me a square matrix, right? And then I could take NP or numpy dot trace of a square matrix, gives me that number, which is called the trace. So I'll set that T equal to that trace. Then I print T and I get some number. Okay, so a few more things about NumPy arrays. Is that okay? All right.
Can you explain NP dot trace line?
Okay. All right. So the idea is trace should be performed on a square matrix, right? So I want to feed trace the trace method a square matrix, right? So B times A, so that's A transpose times A is a square matrix, right? A, the way I wrote it, wasn't a square matrix. So I just wanted a square matrix to feed it to. So B dot A means take B, do the matrix multiplication B times A. Okay. So
That A was transpose of A, B.
yeah, right. Right. So this is A transpose A, which is a square matrix. So once I have a square matrix, then I can take its trace. Okay.
Yes.
All right. Okay. A few things which live inside the linear algebra submodule. So scipy.linalg. These contain things like determinants and methods for solving AX equals B and decompositions and things like that. Okay. So here's an example taking the determinant. So if I set up an array, and this will have rows 1, 2, 3, 0, 5, 6, 0, 0, 9. Okay. So I imported scipy.linalg as linalg because I don't want to keep, I'll use the shorthand linalg for that. Okay, linalg has a determinant method called det. So linalg.det, feed A into that, and it will give you the determinant of A. And in this case, the determinant is 45. Okay. What if I want the inverse of A? Okay, I'll do a rant about that in a second, but well, there's an inverse method, INV. So linalg.inv, if you feed A into that, it will give you the inverse. And this is the inverse of that A. Okay, now, why do we want to take inverses? Typically, we want to take inverses because we want to solve something like AX is equal to B. Inverses are extremely expensive. So a good practice is to say, do I really need a general matrix inverse? Do I really need to run a general matrix inverse here? Now, this is just a 3 by 3 matrix. It won't kill you to use it. But once they get big in serious problems, taking an inverse is a sign of bad programming. Okay. It means you didn't listen to this rant that I'm giving you right now. Okay. Try and find another way to solve your actual problem, which is AX is equal to B. Okay. So sometimes A is upper triangular. So you can use an upper triangular solver, which is less expensive, a lot less expensive than doing a general matrix inverse. Sometimes A is lower triangular. Sometimes you can factor the matrix A. Yeah, there's a question?
Sir, what about something like Cramer's rule?
Oh yeah, Kramer's rule is just as bad. Taking determinants, taking inverses, Kramer's rule, these are all extremely expensive.
Oh, okay.
Okay.
Thank you.
All right. So having said all of that, how should you actually solve AX equals to B? Well, okay, so let's say we set up our B as 0, 1, 1. We already have an A, so we'll just use that. And I can use the solve. There's a solve for AX equals B, feed it A and B, and it will give you the solution of AX equals B as X equals something. Okay. Now, sometimes you have AX is equal to B, and you have the same A, but you have very many B's that you need to solve for. Okay, you might have, say, different measurements give you different B's that need to be solved for, but you're always going to be using the same A. Okay, in that case, it will be less expensive to do what's called an Lu decomposition. Okay, so you write A as being, A is a square matrix. You write A as Lu, with L is lower triangular and U is upper triangular. And then if we have to solve the system for many B's, we can use these L and U with specialized solvers that will take less work than a general solver. Okay? So maybe if you're only going to solve AX equals B once, maybe you can just use linalg.solve. But if you're going to solve AX is equal to B1, and AX is equal to B2, and AX equals B3, and so on up to AX equals B100, then maybe you want to do it this way that I'm going to show you right now using the Lu decomposition. Okay, so we set up an A that has entries 1, 1, 0, 1, 0, 1, and 0, 1, 1, square matrix. And let's say that B is equal to the vector 1, 2, 1. Now we're going to do the Lu decomposition. This is a very common thing that we do in numerical linear algebra. So there's a routine for doing that. My feeling is that there's pedagogical value to you actually writing a code for doing a decomposition. Okay, you do it once in your life just to have an idea of what's going on, and then you use these optimized codes which people have put into these sorts of modules and libraries. Okay, so the Lu factorization method, Lu subfactor, lives inside of scipy.linalg. So we're going to call linalg.lu subfactor of A. And now it will break A. It will say A is equal to the product of a lower triangular matrix and an upper triangular matrix, the lower one traditionally called L, the upper one traditionally called U. And it's going to shove those two matrices into this variable that we're calling Lu. Okay? So the L and U are saved in this Lu. Now when you want to use it to solve, you say X is equal to linear algebra, Lu subsolve. Now use Lu. So Lu has L and U in it. So A is equal to L times U with B. And then it will solve for AX is equal to B. And then you can print the X, and it seems to have gotten the correct answer. Okay. All right. That's concatenated a little bit, I think. Are there any questions about this? Okay.
Professor, could you sort of explain in the sort of cases where you use the Lu and...
Yeah, sure. Okay, so you might have, say, some sort of an experiment. and the B's represent, say, measurements that are of some kind which have been done. So you have a whole series of measurements, right? And you need to solve X for each one of those measurements, right? So the measurements are the result of something that you want to find called X. Those things that you actually measured, they have a relationship with X. AX is equal to B, right? So now you've got a set of measurements B1, you've got a set of measurements B2, and you've got this whole a whole bunch of vectors BI. So let's say there's 1,000 of them. So now if for each one of, if you solve AX equals B1, and then you, with linalg.solve, so that'll be expensive. Then you'll solve AX is equal to B2 with linalg, and that's expensive, and so on and so forth, right? The other approach is to say, my A is not changing, my B vector is changing, but my A is not changing. So I will say A is equal to LU, and then L is a lower triangular, and U is an upper triangular. And when you have triangular matrices, solutions can be done using back substitution, which is very quick compared to a general matrix solve. Okay? So then you take a hit. It's expensive to factor A into L times U. But once you've done that, then using LUX equals B1, LUX equals B2, LUX equals B3, those systems can be solved very quickly. Okay?
Understood, sir.
Right? So in the case where your A is not changing, but you have many B's, this is an approach to use. Okay? All right. So other decompositions that get used in different contexts are singular value decomposition, Cholesky decomposition, and what's called QR decomposition. Okay, by the way, we have a full course in numerical linear algebra. Some of you might want to take that sometime if this part of things interests you. Okay, yeah, so all these methods live in scipy.linalg. I don't want to go through them. The idea is somewhat the same. Okay. Once again, another example when not to use a general solve. A is upper triangular. If it's upper triangular, this can be done with back substitution, right? And so instead of using linalg.solve for an upper triangular matrix A, you want to solve AX equal to B with A as an upper triangular. Use X equals linalg.solve sub triangular A comma B instead of just solve. And it will use back substitution to do the problem, and it will do it much quicker and with fewer floating point operations. Now, when you do this, you're going to, it assumes that you're feeding it an upper triangular matrix, right? So the parameter lower is set equal to false. It's not lower, it's assumed to be upper. If A was lower, then you need to set the default lower value to true. So now if you do a lower triangular matrix A and you have a B and you want to solve AX is equal to B, again, use linalg.solve subtriangular AB, and now set the parameter lower equal to true, and it will solve it. Okay. Is that okay? All right. Another thing that's useful are matrix norms when you're talking about conditioning of a system. there are different types of norms. One is called the two norm. That's the one that we're used to. So if we have a vector x, y, z, then the two norm is x squared plus y squared plus z squared, and then you take the square root of that. That's called the two norm. Okay. So if I just ask for the norm, it defaults to the two norm. So you say n equals linalg.norm of this array x, and you can print that, and that's what you get. Okay. There are other norms. One is called the Frobenius norm. So if you wanted the Frobenius norm, you have to put that in as a parameter, and we use Fro for that as a shorthand for Frobenius. If you wanted the one norm, well, say comma one. If you wanted the two norm, well, that's the default anyways, but if you insist, you can put in two as a parameter. And if you want the infinity norm, that's basically the absolute value of the largest absolute value in the array. Then that's the infinity norm. So you have to give it the parameter infinity. And again, there's an idea of infinity in NumPy, so np.inf. Okay. Now, again, something that comes from measurements, for example, you want to solve a system, you have ax equals b, but you have more linear equations than unknowns. So A is not a square matrix. Okay, so if you have ax equals b and you multiply on both sides on the left by A transpose, then that gives you the normal equations. A transpose AX equals A transpose B. So the system you have is AX equals B, but this has more equations than you have unknowns. The system is said to be overdetermined. Then the normal equations for that are A transpose AX equals A transpose B. And then that can be solved for. So you can tell linalg that you want to solve this using this least squares approach, using these normal equations instead of the original equation ax equals b. Again, this can come from taking more measurements than you have unknowns, for example, might give you something like this. Okay. Now, the result of running the least squares method is to give you a lot of information in an array. The first thing in that array is the array that you want, your X. I'll leave it to you to look at the documentation for the other information that it gives you. So you have A, you have A, B. Now you tell it A comma B, you feed that into the least squares method, and it will give you some result. And then you take that result is actually an array of things, and that the first element in that array is the array that you're looking for, X. So you can say X is equal to result of 0, and that will give you the vector that you were looking for. Okay. All right. Another thing that we often want are eigenvectors and eigenvalues. So when we have AX is equal to some lambda X. So when you multiplied A and X together, you got back X multiplied by some value lambda. So we want the eigenvalue and the eigenvectors, which are associated with the square matrix A. These can be complex. Okay, so the method scipy.linalg can be used to do this. So if I construct a matrix with a square matrix with rows 1, 2, and a second row 4, 5, and I feed that A into linalg.ig, what does it do? It gives me an array which consists of arrays, right? And the first array consists of the eigenvalues. So there's an eigenvalue, and then there's the second eigenvalue, and then there's the first vector. This is the vector associated with the first eigenvalue, and then there's a second eigenvector, and that's associated with the second eigenvalue. Is that okay? Right? So Eig spits back the first thing that it gives you is the eigenvalues, and the other things that it gives you after the eigenvalues are the eigenvectors. Okay. What's the product of the eigenvalues? Do you know what that is? Anybody remember?
Determinant of
Yeah. Okay. Okay. What if I just wanted the eigenvalues? So sometimes it's just, you know, I don't want to, for whatever reason, I don't need the eigenvectors. I just need the eigenvalues. So scipy.linalg eigenvals would give you that. So if you feed a square matrix into eigenvals, then it will give you the two eigenvectors of this square matrix. And I hope that that's clear. And once again, these things are, in principle, these are complex numbers. So it's returning complex numbers too. You'll recall that, okay, so exponentials of a square matrix are important when you're solving systems of differential equations, for example. They can be useful. So the exponential of A, of a square matrix A, is defined as this Taylor series. Identity matrix plus A squared over 2 factorial plus A cubed over 3 factorial, and so on. So if you say linalg.expm, M standing for matrix, it means, if you just said exp of A, that would mean element-wise, give me the exponential of each entry of A. If you say expm, it means I want the matrix exponential. So you have to give me this other thing. So if you feed that into expm, then it will give you the matrix exponential of A. Okay. There are also matrix cosine and matrix sine. Those are cos M and sine M living inside of linalg. Okay. Any questions before we quit?